Okay, so what did we just argue? Well, we argued that if you obey the Cauchy-Riemann equations, you are complex differentiable. And in fact, the Cauchy-Riemann equations have been studied a lot. And if you've got a solution to the Cauchy-Riemann equations, it can be written in this form. So, solution to the Cauchy-Riemann equations, you know enough to check this. So check this in detail. Our function f must be a function only of z. So you could imagine that this is some sum from n is equal to naught to infinity of Cn z to the n. So I've just given you a very, very quick introduction to the Cauchy-Riemann equations. There's many other things that you could read about, and you should also play with these equations, get some familiarity of them with them. And what I would say is one of the first things you should do is take f of z equal to a sum over n c n z to the n and make sure that this obeys the Cauchy-Riemann equations. Make sure you can do it. You should be able to show this as a solution. Now, it's great because if we know um, a solution to Cauchy-Riemann, that implies we know a solution to the conformal Killing vector equations. Okay, so that's why we're interested in solutions to Cauchy-Riemann. They tell us about solutions to the conformal Killing vector equation. So immediately, if I was to set zeta 1 plus I zeta 2, this is equal to some sum from n is equal to naught to infinity of Cn, and we will have x1 plus I x2 to the power of n. So what does that mean? We've solved, well, this is a solution to the conformal Killing vector equation. Zeta 1 and zeta 2 will solve the conformal Killing vector equation, but it means that this solution, so it is solution to the conformal Killing vector equation, and I want you to notice it has an infinite number of parameters Cn. Okay, so let's first of all talk about what does that mean. And to see what it means, I want you to recall something from Poincare. So what I'm going to write in red here was all stuff that we derived when we were studying the Poincare transformations. In that case, we also had a solution for the conformal Killing vector. So it's for the Killing vector. So it's nice to compare the two. We had a nu plus omega nu x nu. And if you remember, we said there were dA nus, there were d of them, and we said that there were d times d minus 1 over 2 omega nus. So if we were in 3 plus 1 dimensions, we would have had 4a nus. We said these correspond to translations, and we would have had 6 omega mu nus, and we said these corresponded to Lorentz transformations. So for every free parameter that we had in our solution, we had a different transformation. Now, with the conformal transformations, our free parameters are Cn. We can adjust those freely. So we have an infinite number of different conformal transformations in d is equal to 2. Okay, so this is special to 2 dimensions, that we have an infinite number of conformal transformations, but that's the case. That's just the way that it is. Now, where would you ever use conformal field theory in 2 dimensions? Well, it turns out that this is the world sheet theory of a string. So if you have some quantum string, the quantum field theory defined on the world sheet of the string would be a conformal field theory. And the fact that the conformal group is infinite is very important for the string. So that is a fascinating subject to discuss further. We're not going to do it in this course. We'll see. Maybe we'll do it in some other course. Um, So anyway, let's try to get some insight into why should the conformal group be infinite dimensional. So from what you've seen so far, there's a deep link to complex analysis. So it makes sense to use new coordinates, complex coordinates. Let's take z is equal to x1 plus I x2, and let's take z bar to be x1 minus I x2. So we're going to think in terms of z and z bar. Now, if you remember, our metric ds squared, this was in Euclidean space, it's dx1 squared plus dx2 squared. And you can see very easily, this is nothing but dz bar. Now, the Cauchy-Riemann equations tell us that we only depend on z. So if we were going to do a coordinate transformation consistent with the Cauchy-Riemann equation, so that means a conformal transformation, we could take the new coordinate z prime to be any function of z. And then at the same time, z bar primed would be some function of z bar. And let me call this f bar just to distinguish the two. And now what I'd like to know is, what does the metric become? So in the new coordinates, we can work out what is dz prime, and this is df dz. So in writing down this equation, let me just stress, I use the Cauchy-Riemann equations because that's what tells me that f only depends on z and not z bar. And in exactly the same way, dz bar primed is equal to df bar dz bar dz bar. So now we can work out what the coordinates are in what the metric is in the new coordinates. So let's do that now. Good. So the metric will be ds squared is equal to dz prime dz bar prime, and this is just df dz times by df bar dz bar dz bar, and let's make that bar a bit more explicit. And what is this equal to? Well, this is just df dz df bar dz bar multiplied by dz bar. And if you compare this answer to this answer, you can see that indeed this transformation has just rescaled the metric. And we said that's exactly what a conformal transformation should do. So if we take z into any function of z, that gives us a conformal transformation, and that verifies for us, hopefully it gives you a little bit of insight into why the conformal group is actually infinite dimensional. There's an infinite number of different transformations that we can do. So of course, the group is infinite dimensional. The Poincare group was also infinite dimensional, but the Lie algebra of the Poincare group was finite dimensional. There were only 10 generators in 3 plus 1 dimensions. Now we'll find that the Lie algebra of the conformal group in 2 dimensions is also infinite dimensional, and hopefully this little computation over here gives you some insight into why that's the case.